number one because people gave answers that sort of made sense to me. But what I was looking for there is in circular motion, the relationship between angular velocity and angular acceleration is that they're parallel. If the rotation is speeding up, they're in the same direction, and if it's slowing down, they're in opposite directions. Okay. In three-dimensional motion, just general three-dimensional motion, they're in general not parallel. You can have angular velocity vector around this axis and an instantaneous angular acceleration about this axis. Okay, but in circular motion, they're either this or this. Then the second one, this should be fairly easy to remember. But this equation that comes up all the time, the watermelon equation, all ripe watermelons will rot. So this represents a circular or spherical motion around a point, and you can break it up into two pieces. This one is the tangential acceleration, and this one is the centripetal acceleration. Ways to remember that. In physics, you probably learned this formula somewhere along the line for tangential acceleration. You can see that this is just a vector version of this. And for centripetal acceleration, somewhere you learned this equation, and it's the same deal. This is a vector version of this formula that you've heard before. Also, I mean, if you couldn't, you forgot, you didn't want to look it up, just do the, choose a point and do the calculation. Say the thing is rotating this way with an angular acceleration also this way, so it's speeding up, right? Well, the tangential acceleration should be tangent. The centripetal acceleration should be toward the center. And so you can actually just come up with, geometrically draw this out, come up with sensible values, and it'll tell you which one is this and which one is this. Well, one thing is for sure, nobody is going to get this question wrong again in this class, because I'm not going to give it again. But you should. But that's a good thing to keep in mind. So, and then 3, what type of coordinate system must the acceleration be expressed in order to use Newton's second law? A lot of people put non-inertial coordinate system. You're thinking in the right place, but it has to be an inertial coordinate system. Non-inertial is when you have to use relative motion equations and compensate for the fact that, so non-inertial is Jamiroquai. Actually, someone drew Jamiroquai and still wrote non-inertial. So inertial coordinate system, that's what you need for Newton's second law. And then the fourth one, what does it take to make something non-inertial? So what are the things that can be happening to a coordinate system so that you can't directly use Newton's second law with those measurements? There's two possibilities. It can be either one or both, and then the thing is non-inertial. Acceleration of the origin. And any kind of rotation of the axes. A couple people put motion of the origin and rotation of the axes. Well, that's not really enough. The coordinate system can be moving with a constant velocity as fast as you want, and it still is an inertial coordinate system. It's only if the origin is accelerating that it causes problems. So, like for example, in that Jamiroquai video, if it was a huge room, it wouldn't work very well with a normal size room. But imagine it was a huge room so that it took a while for the walls to run into him, okay? And the walls were moving with a constant velocity around him, okay? It would look like he was just sliding across the floor, right? Does everyone remember what I'm talking about? It would look like he's just sliding across the floor. But if you use the measurements that video camera took and applied Newton's second law, it would look like the laws of physics held perfectly well. Okay, so it's not motion of the coordinate system that's disallowed, it's acceleration. But then with rotation, it's any kind of rotation. So it doesn't have to have non-zero angular acceleration. As long as those axes are changing directions, if you take the measurements in a coordinate system like that and run them through Newton's second law, it looks like it doesn't hold. We'll spend a lot of time later on why that is. Why is it that changing orientation of the axes messes up the laws of physics? And it has to do with taking derivatives, actually. It doesn't have anything to do with the relationship with mass or force or anything. It just has to do with the derivatives. And then the last one, okay, this one. This is really important, and it's so like, I think we talk about things so many different ways and different ways of doing problems that you just get turned around backwards. But this is just so simple. Acceleration is the derivative of the velocity with respect to what variable? Time, okay? If you know the velocity as a function of time, or the position as a function of time, you can just always take the derivative. In an inertial coordinate system, dp dt is equal to v, and dv dt is equal to a. Okay, so that's always true. If your measurements are in an inertial coordinate system and you have p or v represented in terms of time, you know you don't have to do anything fancy to get the other variables. It's also true, and I'll bring this up again in a second, that derivative of the angular position with respect to time is equal to angular velocity, and d angular velocity with respect to time is equal to the angular acceleration. This is true with these represented as vectors. This one, you can't talk about d theta dt equal to omega in terms of vectors because theta can't be represented as a vector. All right. Any questions about anything on the test? Anything that confused you? Yep. Yeah. Yeah, that's right. So in number 2, the object's moving through this path, okay? And so this path is parameterized by position equal to x squared. And so a unit vector in the direction of motion you get by taking the derivative with respect to the parameter. So you get 1, 2x, right? But now, so this is the place where, I mean, half of the people, and maybe a little more than half did this right and half missed this. It's sort of a subtle point. But this is a vector in the direction tangent to this curve, but in the direction of increasing value of the parameter. So, so basically, there are two vectors that are tangent to the path at any point, right? One's going this way and one's going the opposite way. When you take the derivative with respect to the parameter, that gives you a vector that is tangent in the direction of increasing x in this case. The problem said decreasing x, and so the vector you want is this and this. It's just -1 times the vector. Yep. Over here? Yeah. It's still the same. If you take the derivative, plug in the x value, it gives you the vector in this direction. So multiply that vector by -1 and you get this. So let's take the point, what's one where we can, okay, so let's do it at the, let's evaluate u at x equals -1, okay? If we don't have these negatives on here, we get 1, -2, right? The vector 1, -2 is pointing this way in the direction of increasing x, right? But that's not what we want. We want the one in the direction of decreasing x. And so to get that, we multiply this vector by -1. You know, like if whatever vector you have, if you wanted to switch direction, you just multiply all the components by -1, multiply the vector by -1, and that just switches where the head and tail are.
That would make the y component of the vector positive still. So if it was -2 and you multiplied by -1, then the y component would always be positive.
So if you, okay, so let's think of it for x equals -1 with the negatives on there, okay? So put in -1, you get an x value of -1, a y value of +1, and so that gives you a vector that's in the second quadrant like we want it to be. I'm plugging in the -1 for x because that's the point we're evaluating. And that makes the y component positive.
So then why, but in actually, y would be positive on both points.
Well, if you did it over here, if you did it for x equals +1, you'd get a value of -1 for x, -2 for y. So it would be pointing down into the third quadrant, which is what we want. Any other questions? So yeah, I mean, the basic idea is you take the derivative, it gives you the vector pointing in the direction of increasing parameter. If that's not what you want, then you just want the opposite vector. So multiply the vector by -1 and you have it. Okay. So now we're done just talking about particle kinematics and kinetics. We're going on to collections of particles and rigid bodies. And we're going to see, so now all of these objects have length. It's not just like masses sitting at a single location. So now the objects we're going to isolate have length. And we're going to usually break up the motion. So let me, I guess, say what happens when these bodies have length is where loads are applied matters now. It didn't used to matter because we assumed that it was always acting at the same point. But now, if the objects have length, the location of force application matters. And that brings up the rotational equation, the moment equation. Usually, we're going to break up the motion of rigid bodies into a translation of the center of mass and the information about this translation is going to come from Newton's second law. And then the rotation of points about the center of mass. We're not always going to do this, but this is sort of a general, this is approach that you always could do. This always works. I'll give you one other way to do it that simplifies things in the cases that you can use it. Okay, so first, what can we say about general collections of particles? So think of this as like a blob of pudding. So if we want to do pudding physics, what holds? What equations can we use? Well, the sum of forces, external forces on the pudding is equal to the mass of the pudding times the acceleration of the pudding's center of mass. That's kind of cool. I mean, like, you don't know very much about pudding, and you still get this useful equation out of it. Like, we can actually calculate the acceleration of pudding based on the forces you apply to it. Even though a force would just rip right through the middle of it and the rest would splash off to the sides, this equation still holds. Okay? So what about, so now, you know, we're feeling confident. What about rotational information? Well, for rotations, there's not very much useful you can say. The stuff you can say relates to the angular velocities. So it relates to angular momentum of each individual particle. So you'd have to know something about the motion of every individual pudding molecule in order to say anything about the rotation. So that doesn't help much. You don't want to sit there trying to do physics on a billion particles. And so this, the lack of information that we have about rotations is why we're going to go from talking about pudding to talking about rigid bodies. Okay, so this leads to the rigid body approximation. Obviously, not everything can be approximated well as a rigid body, but a lot of things can, especially engineering materials. And so when we simplify, so when we make the rigid body assumption, here's what we know about a rigid body. Now, instead of one useful thing, that Newton's second law of pudding, Newton was a very firm believer in the importance of pudding in your diet. That's why they named Fig Newtons after him. It's like pudding, I don't know. Okay, so now we know two useful things. Yeah, right, that's a quiz question. The first is we still know Newton's second law. So the sum of the external forces is equal to the mass of the rigid body times the acceleration of the rigid body's center of mass. But now we know something about rotations too. We know that the sum of the moments, I'll say about the point A, on a rigid body is equal to the moment of inertia of that body times the angular acceleration about A. No, I got those switched. So the moment of inertia is calculated about the point A. The angular acceleration, that doesn't have a point. That's just a general property of the body. Okay, so we saw this. I mean, this is just like what we knew in statics. We have Newton's second law before we didn't have the right side, and we had the rotational equation before we didn't have the right side. In statics, what about points could you choose for this relationship to hold? They had to be the same, that's all. But they could be any point, right? As long as A was equal to A. Well, this A wasn't here. It could be any point, right? That's not true anymore. So in a way, like doing this stuff first in statics kind of spoils you, so you have to be really conscious of this. In order to use this equation in dynamics, this is true for a point A if the point A is fixed on the body and in an inertial coordinate system. So the only way you can use this point A, well, there's another way too. So you can do it for the center of mass too. And let me come back to A in a second. So add up all the moments about the center of mass. That's equal to the moment of inertia about the center of mass times the angular acceleration. If you're not using the center of mass, this equation of motion only holds for a point A that's like a pin joint connecting the body to the floor, to the ground, or a ball and socket joint if it's moving in 3 dimensions. Okay? It has to be holding that point fixed in space while the object rotates around it. Okay? That's the only way. Okay, so here's an example. So say that you had a rigid body like this rectangular shape, and its center of mass is here, and it's connected to the ground by a pin joint. So I'm going to call this point A. Okay. In this case, you could use either one of these two approaches and get the right answer. Okay. You could use MA is equal to IA alpha, or you could use MCOM is equal to ICOM alpha. You have the option because here we have a fixed point, and the center of mass thing is always true. You can always use this. Yep.
So it doesn't matter if the center of mass is inertial or not.
The center of mass is not, that's not the origin. So it does matter that the origin is not accelerating, but the center of mass can be accelerating.
Because if the object is free space,
Yep.
it'll always rotate around the center of mass.
The body will, yeah, that's right. So let me give you an example where you have to do it about the center of mass. So say that you have a boomerang flying through space. Anyone have a sense of where the center of mass of the boomerang would be? Right about here, that's right. So remember that there's no rule saying that the center of mass has to actually be on a material point, okay? So in this case, there's no point on the boomerang, since it's flying through space, there's no point on the boomerang that's fixed in any inertial coordinate system. So in order to do rotational calculations with this, you need to use that the moment about the center of mass is equal to the moment of inertia about the center of mass times the angular acceleration. There's no point. So if you had this, if you nailed, right, there's no point on it that's staying in place in any inertial coordinate system.
What if it's a shape like where there's a point that's moving but it's not, or I don't know how to explain it, like there's a center point that's just rotating but it's not moving, or
Right.
it could be translated.
Yeah, if
If
it's not accelerating,
yeah. Use that point.
yeah, that's fine. Then you just have to use a coordinate system
So it doesn't
moving with it.
It doesn't have to be attached, it just can't be.
Oh, it has to be attached to the body.
But it doesn't have to be
Oh, it doesn't have to,
attached.
right. If there's some other reason other than a pin joint, if there's some other reason that it's fixed in space,
Like you just
then
have
that
to
would be
rotate
fine.
it.
Yeah, that's right. So like, for example, you could do calculations if a car, or let's say a train was moving with a constant velocity. Then if you put your coordinate system on the train, you know, then there's a point on the train, maybe more than one point, where it's moving, where that point is fixed in the coordinate system that's moving along the tracks. So yeah, that's fine. By the way, did you know, this just always makes me think of this. So, you know, high jumpers. Good high jumpers. Okay, so he looks, that guy doesn't look so good, I don't think. Okay, but when they high jump, they, you know, they jump over backwards, curl their back over. You've probably seen that. The good ones actually, when they're maxing out, when they're at the highest they can go, their center of mass at no point during the high jump goes as high as the bar. Isn't that cool? So they get their whole body over the bar, And if you track the motion of their center of mass, it just goes right under. Because like I could draw this a little more exaggerated to make it. So like at every point, like say right here, okay, so right here, even though this much of his body is above the bar, almost all of his legs, his head, maybe his arms are below the bar. And so if you calculated the center of mass, it would be lower than the bar. And that's true at every point. It's just all you got to do is keep getting that one part that's on top of the bar high and the rest low. Okay, so rotational Newton's second law is this, m equals I alpha. Now we have to derive ways of calculating a few things. The location of the center of mass, the acceleration of the center of mass. We have to talk about what a moment is, and we have to talk about what the moment of inertia is. So the first thing I want to talk about is center of mass. I know anybody who just finished statics, we talk about center of mass quite a bit. And I hope that everyone in this class has seen calculations of center of mass before. I'm not going to spend a ton of time on this. But let me know if you want some background on this that I'm not giving. So center of mass. The definition of the center of mass is the total mass times the position vector of the center of mass is equal to the integral over the entire mass of P dm. For a homogeneous material, so homogeneous means that it's the same type of material the whole way through the body. This is equivalent to calculating the centroid. And the centroid, remember, we calculated as total volume times the centroid is equal to the integral over the entire volume of the location times dv. This would be in 3D. And if you're doing a 2D problem, the centroid calculation is the total area times the centroid is equal to the integral over the area times x dA. Okay, so in statics, this was the calculation that we used most of the time because most of our problems were 2 dimensions. That's the definition, but usually we're not going to use integrals. So we won't usually use the integral definition. We'll usually use symmetry or the sum formula. And the sum formula says that the total mass times the position of the center of mass is equal to the sum going over all the discrete individual pieces of the mass of each individual piece times the position of its center of mass. And if the material is homogeneous, then that reduces to the centroid formula that says in 3 dimensions, the total volume is equal to the sum of the individual volumes times the position, or times the individual centroid locations that's in 3D. And then in 2D, it's just the area version of that. So A total times the X centroid is equal to the sums of AI times X bar I. That's the 2D version. So as far as symmetry, yeah. Anybody have any questions about this yet?
The sum of M total, or M times the points, is the sum of.
So if you have it broken up into this piece, and this piece, then say this is 1, 2, and 3. So this is the mass of that piece 1 times the centroid of piece 1, or the center of mass of piece 1, plus the mass of piece 2 times the center of mass of piece 2.
So N is just number of pieces.
Yeah, that's right. Yep. Okay, so symmetry. In 2D, the centroid of an object always lies on any line of symmetry. And that means that if you have 2 different lines of symmetry for an object, you find the point where they intersect, and that's the centroid. So that's easy. So if you have 2 non-parallel lines of symmetry, the centroid lies at the intersection. Okay, so for example, a rectangle has a line of symmetry like this, and a line of symmetry like this, and so the centroid lies right at the middle. A circle has a line of symmetry like this, a line of symmetry like this, infinitely many, but they all go through the center. So take any 2 of those, find where they intersect, and that's the centroid. And then what about something where you can only find 1 line of symmetry, like the boomerang? Well, it has a line of symmetry like this, but you can't find any other lines of symmetry. So all you know is that the centroid lies somewhere along this dotted line. But that still gives you some useful information, because then you just have to find the y location of the centroid. You don't have to find the x also, you know. In 3D, the centroid lies on any plane of symmetry What type of mathematical object do you get when two planes intersect? A line, yep. And so finding where two planes of symmetry intersect isn't enough to specify the centroid, right? But if you take a third line and intersect it through those two, those three planes intersect at a point, and that point is the centroid. So if you can find, so if you have three non-parallel planes of symmetry, then the centroid lies at the intersection. Okay, so let me give you a couple of shapes that are going to come up in this class that you'll need to calculate centroids for. So here are a couple simple shape centroid formulas. First, a semicircle. This is a line of symmetry. So we know that the centroid is going to lie at the midpoint along the, the flat line through the diameter. But what we don't know is the height. And so the height of that centroid is given. So if you call this y bar, that's equal to 4/3 r over pi. And to use this, if you have a complicated shape that's made up of a lot of shapes, you need to know the areas of those individual shapes. And so the area of this is pi r squared over 2. And then a right triangle. How many lines of symmetry are there in a right triangle? If it's isosceles, there's one, but in general, there are none. So I need to give you a formula for both of these two locations. So I'll call this x bar and this y bar. So if this is the height h and this is the base b, then x bar is equal to b over 3. Y bar is equal to h over 3. And the area of the right triangle is equal to 1/2 bh. And then I guess I'll just leave it there for now, but I'll put a sheet up on D2L that has a few other formulas for some other shapes, so the same one that I gave you in statics. Okay, so let me do an example. So let's say that we have a plate with a height of 1 meter and a length of, oh, well, it's a square, I guess. Make it look more like a square. Yeah, it's topology. So we'll make the, so now we're going to remove a circle from that square. I'm going to call this body 1 and this body 2. So this shape is a circle removed from a square. And if you say that the thickness over the whole shape, so this is the material, the shaded region is the material region. And there's this hole in it. And let's say that the thickness through the whole thing is 0.1 meters. And the density of this material is 5,000 kilograms per meter cubed. Anybody remember what the density of water is? 1,000, yep. So this is denser than water, so it's something that'll sink. Anyone remember? Are you disputing that? You don't believe that? I thought you were just going to be like, we'll have to agree to disagree on that. Okay. And then what about steel? Is this denser or less dense than steel? Metal in general. Well, some are way lower, but steel is 7,000. So this is less dense, yeah. It would not sink into molten steel, that's true. Okay, so how are we going to figure out where's the center of mass? What's our strategy? Well, one thing, notice that there's a line of symmetry. So that means that if we use a coordinate system, say we put a coordinate system here like this, we don't have to figure out the y height. That we can just get from symmetry. We just have to figure out the x location of the center of mass. So that cuts the amount of work in half. And our strategy is for the x centroid, the total mass times the x centroid is equal to the mass of body 1, the square, times the centroid of the square, plus the mass of, no, we're removing it, so we have to subtract the centroid, we have to subtract the mass of the circle times the centroid of the circle. It is 1/4 meter, I guess, because it comes out to the midpoint. That should be quite clear from my wavy square drawing. Okay, so for piece 1, the volume is 1 meter times 1 meter times the thickness of 0.1 times the density. And so you get 500 kilograms. And the centroid is, so if this is our coordinate system, what's the x coordinate of the centroid of the square? Yep. And then for piece 2, the what?
You said mass, the volume times density.
This is the volume here.
You just wrote V equals everything.
Oh, thanks. Yeah. So that's the mass, yeah. And piece 2, the area is pi, the radius is 0.25, so pi r squared, then times the thickness, and then we're multiplying that by the density. So you get a mass of 98.17 kilograms. And where's the x location of the circle centroid? So 0.5 to get here. Yeah, another 0.25 to get here. So x2 is equal to 0.75. And so the total mass is equal to 598.17 kilograms. And so the centroid formula, or the center mass formula, says 598.17 times the center of mass that we're looking for is equal to 500 times 0.5. Oh, I should have subtracted, not added. Sorry about that. So 401.83. Minus 98.17 times 0.75. And you get an x location for the centroid that's equal to negative 0.061. That's in a different coordinate system. Can someone, so what would that be? 0.49. Yeah, can someone calculate that? What is it? 0.439, okay, meters. The y centroid from Symmetry was equal to 0.5. And so the position of the center of mass is 0.439.5. Any questions about that? Okay, I want to show one more thing, and then we'll take a break. So this is something that's going to come up a lot because, so notice, the position of the center of mass doesn't come into Newton's second law. But the acceleration of the center of mass does. So based on that centroid, or that center of mass formula, how do you go from the location of the center of mass to the acceleration of the center of mass? And I'll show it for velocity too. Well, if you think of taking that center of mass equation, so the total mass times the center of mass location is equal to the integral over the mass of P times the increment of mass. What happens if you take the time derivative of both of these? Assuming that the mass isn't changing, and assuming that, so yeah, if you assume that the mass doesn't change, then take d dt of both sides. It gives you two formulas. The first one says the total mass times the velocity of the center of mass is equal to the integral over the mass of v dm. And you can also use this with the sum formula. So the total mass times v com is equal to the sum for I from 1 to n of the individual velocities of the center of mass times the individual mass. And if you take a second derivative, you get that m total times the acceleration of the center of mass is equal to the integral of the acceleration dm and that also holds for the sum formula. So the total mass times the acceleration of the center of mass is equal to the sum from 1 to n of mi a comi. Okay. Yep.
It's just like bookkeeping. Why do you do a different M for each of them just because the subscripts? Or?
For which one?
Well, you have a lowercase m on one side and then of the m total a center mass equals.
Where is it?
Never mind.
This?
I was wondering about mi versus capital. Yeah, I was wondering why it was capital and lowercase m.
Oh, those should be the same. I guess I'm just used to writing my limits of integration with an uppercase for the whole body. But yeah, that's the same mass. Yes, that's a good point. And notice one other sort of useful thing about this formula. the way that center of mass comes up in Newton's second law is as a sum of all the masses. Like it comes up as the total mass times the it doesn't just come up as the location of the center of mass. It comes up on the right side of Newton's second law as the total mass times the acceleration of the center of mass. And so you don't even have to do this calculation. When you have a collection of bodies where you know the individual centers of mass and you know the individual masses, you can just put this sum right into the right side of Newton's second law without the middle step of calculating the centroid. Okay, because this is how it appears in Newton's second law. I'll do some examples like that. Okay, let's take a 10-minute break, come back at 2:19, and we'll go into kinematics. Yeah.